So we'll give people, there's 5 minutes yet to start.
Sure. Not a problem.
I think, are you, Anirban, going to be touching on kind of using the domain as well as data to build models? I mean, when we look at very complex domains, just purely data-driven approaches aren't really going to work, right?
Yes.
So
Or once we have the data, there are more things to do actually than just analysis. So that's what I want to hit upon.
Great, super. So I know one of our common friends, I don't know whether you know that Deepiman also gave a webinar a while ago here at Sabudh.
Okay.
And it was very well received. He was talking about the difference between correlation and causality.
Right.
It's a topic that doesn't get enough airwaves. I think the whole deep learning wave has made that silenced that voice to quite an extent, at least in the industry.
Right.
But it was really nice to hear from him on that.
Yeah. We are working on a problem in economics with these type of things actually, where you have to worry about causality, and
Right.
because in economics it becomes very important to know which variable is affecting what, but then it is not easy to untangle these variables. Sometimes more than one variable is influencing a particular one.
Right.
I
think there is a lot of pushback now in the AI community as well, that explainability is equally important in any domain, right?
Correct.
And especially some of the deep learning work where the models are black boxes.
Yeah.
It's very worrying, and of course, we were talking offline about ethical concerns and so on and so forth.
I'll switch off the thing because otherwise it makes noise. Yes. Yeah.
Okay. Right. So I think what the community is realizing is that some level of explainability is important in every domain, and being able to also root it on domain dependencies is an important aspect of any model that we build of a real world process. So it's great. Okay, so Anirban, it's coming up to 10:30. So first of all, thank you so much for taking out the time on a Saturday morning to speak to all of us. It's indeed a pleasure to have you here. For those of you who are unlucky enough to not have heard of Anirban already, Anirban has more than a couple of decades of research experience, and that too across the world, right? So he has made a great name for himself with the wonderful research that he's been doing. And, it truly is, to me, I think what modern education has done is to take away a lot of the cross-disciplinary learnings that used to take place. And if you look at Anirban, clearly he's found a way to make sure that did not affect his life. So he's got research interests in econophysics, sociophysics, terms that most of us don't even necessarily understand, and then data science, complex systems, statistical physics, quantum physics, and nanomaterial science. So, and this too, researching in Paris and other parts of Europe as well. So, you're a real role model for the kids that are learning in Sabudh. as to what is possible. So we'd love to hear a little bit about how you made this happen for yourself, and then of course we'd love to hear about the topic itself, which is very intriguing. How to bridge data and science for deciphering complexity. So Anirban, thank you again for taking out the time here, and we look forward to hearing you speak. Over to you.
Thank you, Sabudh, and I'm really humbled by your introduction. Very kind of you. And so, as you told, I will actually share my experience and my journey. So, is the screen visible now? Yeah. Okay. So,
yes, it is.
Right. So, I'll be talking about bridging data and science for deciphering complexity. And so I wanted to spend a little bit about my background, but before that, I must thank my collaborators. Actually, I have many collaborators whose names I haven't been able to put up here, but the work that I will be showing mainly have been done with some of my students and colleagues. So Kiran Sharma, Dr. Kiran Sharma is now a postdoc in Northwestern. She was my PhD student, and most of the work I've done with her. Richie was a master's student, has now joined PhD in GNU. Adarsh Mishra was also a master's student in GNU. Rajdeep Haldar was a master's student in ISER Pune. He is now in the US in Purdue University. Shorish Dash is my collaborator. He's a statistician and works in Chennai Mathematical Institute. Shubho Bakar is again a statistician, and he works in the CSIRO in Australia. Anindo Chakraborti is an economist working in IIM Ahmedabad. And Rakesh Chatterjee, Hirdesh Parasi, François Lefra, Thomas Seligman, they are all physicists. And Arijit Samal is a computational biologist. So you will see that I've worked on various domains and interdisciplinary subjects. And so I really work with social scientists, and biologists, and statisticians, computer scientists, and so forth and so on. So I want to share a few of my slides on my background. And so I was born and brought up in Darjeeling, and this is the typical night view. This photo was clicked by one of my friends, actually. And you will see that, this night sky is beautiful. And if it reminds you of your nursery rhyme, Twinkle, Twinkle, Little Star, how I wonder what you are. And I would like you to focus on these two words, how and what. So what you'll find is that in the research thing, you have to make observations, and you'll be looking at, things which will tell you what they are. And then you have to start wondering how, and that's where the science comes in. And that's what I will be focusing on, how and what. So I'll be bridging that data and the science to answer these type of questions. So as I told you, I went to the schools in Darjeeling, which are very famous. One was St. Joseph's Darjeeling, which was a Catholic school, a Mount Hermon school, which was a Protestant school. And I spent the first 18 years of my life there. And then I moved to Kolkata, and I started doing my bachelor's at the Scottish Church College. Again, they're one of the oldest colleges in Calcutta. And legendary persons like Netaji Subhash Chandra Bose, Swami Vivekananda, and many other philosophers have been students of this college. Then I went for my master's to University of Calcutta Science College. Again, we had very legendary professors like Satyendranath Bose, Meghnad Saha, C.V. Raman, who was Nobel laureate, and many others. For my PhD, I went to Shah Institute of Nuclear Physics, and that was founded by Meghnad Saha, and later on became famous. When I was in France for several years, I also completed my habilitation, which is equivalent of DSc, from the University of Pierre and Marie Curie. For my postdoc, I spent a little bit more than a year at the Helsinki University of Technology in Finland, and it's a very old school, actually, which has now been called Aalto University. And then I spent 2 years in Brookhaven National Lab in the US, which is again very famous for particle physics and accelerator physics. So you see there's a big accelerator. So this campus is like 10 miles, 15 miles in radius. And this was one of the largest accelerators before the Large Hadron Collider in Geneva was built. So this is to be known as the relativistic heavy ion collider. And again, several Nobel Prizes have come out from this lab. Then I returned to India as a theoretical physicist in Banaras Hindu University. I spent 3 years and then moved to France at École Centrale Paris. So it's one of the Grandes Écoles in France. Grandes Écoles are these specialized engineering schools. You may have heard of École Normale Supérieure, École Polytechnique. These were all established in the regime of Napoleon Bonaparte. And this school is very famous. Like you've heard about Eiffel Tower, right? So Gustave Eiffel was an alumnus. And all the French car makers like Citroën, Peugeot, Renault, they are all ex-students of this school. After spending 5 years, I was offered a professor's position at the Jawaharlal Nehru University, and I joined in March 2014. So I'll be about to complete 7 years in JNU. And there I started this field of complex system studies in the School of Computational and Integrative Sciences. And I'll explain those terms in a while. So I have a small research group, and as I told you that it's very, interdisciplinary and heterogeneous. So Praveen Mishra is doing his PhD. He is working on nanomaterial science. Vishwas Kukreti has a master's in complex systems and he's doing his PhD in econophysics. Alka has a master's in physics and she's working on data science approaches to environmental systems and climate change. Richie has just joined PhD. Will be working on econophysics. And these are some of the former students and postdocs. So Dr. Akshansh Gupta did his PhD in computer science. He used to work with EEG and brain-computer interface. Dr. Amrita Singh has a PhD in statistical physics. Arun Patel in nanomaterial science. Kiran I have already introduced. And Syed Sharik Hussain has been working on social physics. And these terms will become clear again in a while. And recently, we've started an interdisciplinary center called the Center for Complexity Economics, Applied Spirituality and Public Policy in the O.P. Jindal Global University. And we inaugurated in September. And ever since, we've been actually doing a lot of interdisciplinary things. Now, you can ask a question that why complexity economics, applied spirituality, and public policy? And how are the things related? So I'll give you a quote from Gus Speth, a US advisor on climate change, that I used to think that top environmental problems were biodiversity loss, ecosystem collapse, and climate change. I thought that 30 years of good science could address these problems. I was wrong. The top environmental problems are selfishness, greed, and apathy. And to deal with these, we need a cultural and spiritual transformation. And we scientists don't know how to do that. So you may do all the science that in the world, but you will not be able to solve the problems because it requires much more than that. And that's why we want to combine complexity science along with applied spirituality so that we can make effective public policies. Now, we've been holding regular panel discussions on these topics with some of the pioneers in this field. And recently we had a very nice international conference on artificial intelligence in complex socioeconomic systems and public policy. And I really learned a lot. And you will see that in many of the speakers who participated, I have actually learned from their talks and their slides, and I will show you and share my experience from there. Now, 2020, we have all been affected by the pandemic. We were not prepared at all. And as you may have seen, that economic experts have warned that this may lead to a crisis, which may be one of the greatest economic crises since the last Great Depression in the 1930s. And the healthcare workers, the government institutions, administrators, public policy makers, scientists have all been working together to fight this pandemic. But then there was a wonderful article written by two complex system scientists from Santa Fe Institute, Professor David Kakwa and Professor Geoffrey West, and who said that, see, we are not attending really to the main problems. And even though we are trying hard, we're not being able to control because maybe we are missing things. And so they said that the damage we are not attending to, and this article is available on the website. You can take it and have a look at it. And that's a problem actually, that these are so complex problems that you cannot solve so easily. So you will see that in most of the European countries now, there was a second wave and now the third wave, and it's becoming increasingly difficult to actually contain the pandemic, right? In 2008, we had another very great financial crisis, which used to be called the subprime crisis. It was triggered by big banks failing. So like AIG, Lehman Brothers, and Merrill Lynch, all of them crashed around the September 15th, right? And again, the economists could not actually warn us of that crisis. And then there were several criticisms, and I'll analyze those, and I'll try to explain what happens during these crashes and what can we do to monitor such crashes, or if we can forecast these, or how to understand what actually happens during those crashes. Okay. Now, the forecasting based on data has been done for a very long time, for more than a century. So you'll see that this is a paper from 1910 written by Warren Persons. And he was working with this, correlation-based studies of economic statistics. So as Sarabjot was saying, I think Dipoman talked about correlations and causality. So there were this article and the next one, which was on the methods of business forecasting based on fundamental statistics by Brookmeyer. This was published in the American Economic Review in 1913. So they all dealt with such issues. So you see that in more than 100 years ago, people have been doing this type of charts and analysis of charts, data, and even now we are continuing to do so. That time in 1913, and now in the electronic stock markets, globally accessible and globally available data. And so data science has become ubiquitous because, this, and not only in the financial world, but also in economics world. So here, for example, I've taken a slide from Doyen Farmer, who was a speaker in the artificial intelligence conference. And here we plotted 20 years of price changes in the United States for most of the services, so hospital services and college tuition fees and things. So you will see that there are certain things which have, prices have continuously increased and others have gone down. So televisions, computer software, wireless telephone services, these have been going down, but then the most essential services like health and education have been becoming more expensive. Now, if we want to make effective public policies, then we need to do this analysis, and not only for a particular country, but for countries across the world. And some of the problems you will see cannot be solved exclusively by a single country, but it needs the cooperation of all countries, and climate change is one such issue. So as I was telling, data and big data. So you'll see that you have data from stock markets, which are called the equity markets, and you have futures markets, and auctions markets, and different types of things. And so people have been trying to understand the behavior of these futures, for example, along with how the news and the sentiments, influence these prices or not. So machine learning algorithms and NLP have been used to extract news. And there are certain databases like the GDEL databases, which does that, classifies those sentiments from the news, and then tries to understand what these sentiments are they positive and negative. And then people have been studying that how are the movements of these futures prices being influenced by news. Okay, so the news can have different types of sentiment scores, and depending on that, how are the prices moving. So people are studying this type of thing. So you'll see that, as I was telling, that it's not only the financial experts or the mathematicians, financial mathematicians who are working, but they're working in close collaboration with data scientists, so they can understand the movements of such prices and forecast them better. Okay. Now, how big is the big data? So this was another very nice speaker, Carol Piovesan from INQ Law in Canada, and she was talking about ethics in data. And then one of her slides showed that in a typical day, how much data is being exchanged in the world today. like 500 million tweets, and then you're working on WhatsApp, Facebook, and all the social media, and you can understand, these numbers. It's not only in, gigabytes and terabytes and petabytes, and but it's gone to exabytes, and we are having to come up with new and new, measures. So you'll see that the data is becoming bigger and bigger, and how do we handle that data? And of course, that's where you all come in. Most of you are being trained or trained in data science and artificial intelligence and machine learning, and so most of the people are now working on these fields to handle the big data and try to make sense of that. Now, the artificial intelligence field started about 65 years ago in a conference in Dartmouth in 1956. And since then, even this field has been going through many ups and downs. So one of the first foremost persons who actually worked on artificial intelligence in economics was Herbert Simon, who was also awarded the Nobel Prize in Economics. It was on the rise for a long time, and then there was a dip during the 74-80. Again, there was a rise in 1981, and again a dip in 87 and 90, and then 97 onwards it has been increasingly up. So you will see that in each of these fields you have cycles. So you have crests and you have troughs, and that's quite natural in any field. So including in business cycles, so you'll have crests and troughs. Now, at present, for example, the artificial intelligence field is becoming more and more popular because, of course, there's the availability of cheap computation, and so the training time is going down, and the costs are also going down, and that's why you have huge amount of people working on the fields of AI. And alone in India. So this slide is taken from an economist, Saurabh Mishra from Stanford University, and he was talking about how AI startups have come up in India, and only in a single year you'll find in all these fields AIs have been receiving funding, and they're springing up, and this is only the beginning perhaps in India, and we have a long way to go. Right now. You must remember the talk of Mr. Mukul Jain a couple of weeks back. I was attending the talk. Sarabjot, you remember when he spoke about this big data and business analytics markets, and I really enjoyed his talk, and I actually took down notes and also took screenshots so I could share with you. And he was talking of data-driven innovation. And he told that the big data and business analytics would be one of the biggest job of the 21st century. Now, the thing is, all these things in artificial intelligence, machine learning, data analytics are involved. And of course, what is data analytics? Analytics is a scientific process of deriving insights from data. It is extensive use of facts, data, statistical analysis, explanatory and predictive models to drive decisions and actions for business value. So you have the data, you analyze the data, you gain some insights which help you to decide and perform certain actions, right? So that is what he had explained in his talk. Now the problem and a caveat. So this is a cartoon which says, for example, remember the other team is counting on big data insights based on previous games. So kick the ball with your other foot. So in the previous games, this person was kicking the ball with his right foot. So now his coach comes and tells that they have done this analysis and how you've been playing with big data insights. So what you do now, you change your strategy. Instead of kicking a ball with the right foot, you kick the ball with the left foot, right? And so that becomes a problem because none of your big data insights will now be of any use, right? And so that problem. Deal are complex adaptive systems, okay, and that's where you need alternate approaches, right? And that's why I think Mr. Mukesh Jain was also stressing on innovation. So if I have a certain set of tools, techniques, results, formalisms, I still need to continuously innovate, okay? So that's where I want to bring in this concept of bridging data and science. Okay, so there is data, but you also have to understand the science, and that will help you to innovate. Okay, and so the bridging of data and science, that's what I was saying, that decisions are based on data. Good use of statistics can guide those decisions, right? But then you need to understand these things and the appropriate use of modern statistics so that you can solve these complex problems. Okay, and so you need to ask and answer the right questions. That's where the science or the engineering comes into play. Okay, so that's where we need to bridge the data and the science. I told you we have huge amount of data, but then we have to figure out that what are the right questions to ask, and then only we can answer them. Okay, now what is science? So science is a knowledge or a system of knowledge covering general truths or the operation of general laws, especially as obtained and tested through scientific method. Okay, so it's derived from the Latin word scientia, which means knowledge. Okay, now what is a scientific method? This cartoon would try to explain that, this is a child. The child makes an observation. So he finds something on the ground, on the floor, right? So it makes a hypothesis that maybe this is a thing which is eatable or edible. And then it performs the experiment. It takes that object and puts it into the mouth. And once it has done that, it will analyze the data. So it will look at the experience and see the face of the color of the face has changed, the complexion has changed, and it didn't like. So it starts crying, and so that's the report of your findings. Okay, know that this is not an edible, thing. And then what it does, it also invites other kids to reproduce the results. Right? And this is what we do in science. Okay, so sometimes what we do are make simple models. So this one on the left, it's a slide taken from my colleague Matteo Marsili. He spoke again in the conference, and I really like this slide. So originally Ptolemy had made a very complicated model of the universe. Okay, this was many centuries ago. And then what Professor Isaac Newton did was actually look at the data that came up from the works of Kepler and Brahe, and formulated the universal gravitation law, right? And this went on for many centuries till in the first half of the 20th century, when Albert Einstein came and modified the theory of gravitation, and we have a new theory which is called Einstein's general theory of relativity. And so you had to modify those laws in a certain way, because new facts, new observations were made. Okay, and that's when Einstein had predicted that the rays of the sun, that means the light, can bend. So we know that light travels in a straight line. Most of you may have studied in your high school the rectilinear propagation of light. So you think that the light travels in a straight line, but that's not true. Not true. It's true in that in the class 8 experiment that you did. Probably you put some screens, you made some holes, you burnt a candle, and you look for the light on the other side, and then you concluded if these holes are aligned together, then only the light passes from one side to the other side, and that's why you concluded that the light travels in a straight line. But actually, light doesn't travel in a straight line. It travels through the shortest path, which is called a geodesic. And that's why when your space and time have curvatures, it can bend. And what makes the space and time curvature curved? It is because of this presence of very high intensive gravitational fields, which are acting by very heavy or big objects in the sky. So what happens is all these big stars and planet things will be exerting this gravitational field, which will be changing the curvature of space and time around them. Okay, and that will cause the light to actually follow a path which is not the straight line, but a geodesic, or the shortest path. Okay, so the entire theory had to be revised. Okay, now that's how we do science. And one of the most traditional approaches in science is called reductionism. Okay, which means that you try to reduce from a bigger to a simpler or smaller part. Okay, and so one philosophical position is that a complex system is nothing but the sum of its parts, and that an account of it can be reduced to accounts of individual constituents. So that's how actually the subjects of physics, chemistry, and cell biology, etc., normally, progressed in the last few centuries. But then we will find that there are limitations. Okay, so in typically the format has been like, suppose I ask, what are you made up of? Okay, you will say, I'm made up of, cell tissues and bones, right? So your blood is also a tissue. You have, the skin, which is a tissue. So we are all made up of tissues and cells. If you tell that, okay, what are the cells made up of? The cells are made up of different chemical organelles, right? So your DNA. So what is your DNA? The DNA is again a assembly of similar and different nucleotides. What are the nucleotides? The nucleotides are different types of chemicals. So it's basically atoms. Now, what are the atoms made up of? The atoms are made up of neutrons, protons, which form the core, and the electrons, which move around them. Now you can break the nucleus also, and you will find that the neutrons are made up of something called quarks, and the protons are also made up of another combination of quarks. So this way you try to reduce. So the complex being is being reduced to smaller and smaller and smaller parts, and that's what physicists have been studying. So all the particles that are available in the universe have now been classified, and these are called fundamental particles. And there are two groups of particles. So one is called the fermions, which follow something called the Fermi-Dirac statistics. Okay, and the other one is called bosons, and that is what Bose-Einstein statistics. And this Bose is Satyendranath Bose, whom I was talking a while ago, that he was a professor in Calcutta University. So half of the particles in the universe are actually named after Bose and Einstein as bosons. Okay. Now, what are these different particles? Mainly, you can classify whatever is matter are basically fermions, and whatever are forces are basically the bosons. Okay, so the gravitational force, the electromagnetic force, the nuclear interactions like strong and weak interaction, these are all forces and are mediated by particles called bosons. And whatever forms of the matter are called fermions. Now, suppose I give you this. Can you explain how the universe works? Probably you won't be able to do. And that's the limitation of reductionism. So there was a wonderful paper by Nobel laureate in physics, Phil W. Anderson, in 1972. So it appeared in a journal called Science, which said more is different. And there he told, for example, the sciences can be arranged roughly in a hierarchical pattern, like I told you, particle physics, and then you have many body physics, then you have chemistry, then you have biology, then you have physiology, then you have psychology and the social sciences. Now, if you think that I'm a master in particle physics and I'll be able to explain the whole world or the whole universe, so then you are wrong actually. Why you are wrong? Because you will see that at every level of this hierarchy, there are different laws, different concepts. Okay, so at every stage, new laws, concepts, and generalizations are necessary. So psychology is not applied biology, nor is biology applied chemistry, nor is chemistry applied physics. It's nothing like that. Okay, and that's why sometimes what you need is called an integrative approach, and that goes for the opposite direction. So we were coming from a top-down approach. Now we go a bottom-up approach, and that's the approach we follow in complexity. Okay, and that's what we call integrative sciences. So in my own research, I have followed, where I applied statistical physics to different domains and combined all these fields. So maths, computer science, economics, sociology, biology, and many more actually. Okay, and that's what we are calling integrative science. Okay. Now you'll see that if this picture is taken from Wikipedia, and it tells what complexity is, right? And I told you that normally the complexity means that a system is divided into a set of parts. Okay? Now the problem is what is complex is often relative and changes with time. Okay, so there can be things which change with the scale that you're looking at, and the scale can be a length scale or it can be a time scale. Okay, and that's why scientists divide these problems in different types of length scales and time scales, and then different types of studies come. So like I was telling you, when you are breaking this body, so when we are working at the level of atoms, we call it atomic physics. And then that's like 10 to the power of minus 8 meters. And then when you go to the nuclear physics, that's of the order of 10 to the power of minus 15 meters. Okay, and then you keep on breaking. You may have heard about these this string theory. Okay, I don't know how many of you have watched that movie on the theory of everything on Stephen Hawking. So he proposes what are called string theory. So what the string theories propose are that all the elementary particles that you observe in the universe are actually strings which can be either open or closed, and they are vibrating. And these different modes of vibrations are actually the different types of particles that you observe in nature. So ultimately, it's basically a string which is of the order of 10 to the power of minus 31 meters or so. So it's extremely small. So you assume that they are point particles, but even they have a structure which is like a small string. Okay? And then it's a beautiful mathematical theory which tries to explain how the universe is made up of and how the universe works. Okay, it's still not complete. And the second is that there are a lot of experimental verifications needed. We cannot do these experiments with the present day equipment or setup, and so we will have to wait a while in order to verify many of the results which string theory actually proposes. Now, as I was telling you, all these systems that we are now going to talk about will be complex systems, okay? And for example, our society is a complex system. Why? Because each individual in the society is very different from one another, right? So we are very diverse. The interactions among the people are very diverse. And not only that, that interaction changes over time. Okay, so when I first met Sabudh, maybe I was very formal, and then as time goes and we interact often now, things become more informal. Okay, and the way I will behave with Sabudh, maybe I will behave with my student Richie in a different way. Why? Because Sabudh is my colleague and my friend, and Richie is my student. Right. So the interaction will be varying. Now, in physics and in chemistry, we are often used to handling large number of molecules or atoms, right? Typically, in a one glass of water, there will be 10 to the power of 23 molecules of water, right? That's the Avogadro constant, right? The Avogadro number, which you studied in high school, right? So typically in a glass of water, you'll find 10 to the power of 23 molecules. But what is good is that each and every water molecule has the same structure. And that's what we chemically represent as H2O. So two hydrogen atoms and one oxygen atom. And you will find that these two hydrogen atoms will be at in a slightly angle to the oxygen atom. And that's why you will be able to explain most of the physical or the chemical properties of water. And typically what we do is what you have studied already in your high school is thermodynamics, right? So you talk about the average properties which can be experimentally measured. So you have pressure, you have volume, you have temperature, this can be experimentally measured, right? And then you studied, the ideal gas law, which is like PV equal to RT, which connected the pressure, the volume, and the temperature of the ideal gas, right? And so these were thermodynamic variables, and you could find empirical relations connecting these thermodynamic variables. Now, for these complex systems that we will be talking about, often you will not be able to make such, average, pictures or thing. And second is that it is very difficult to find such an equation of state. Okay, and therefore there are different ways of approaching or studying the complex systems. Some of these are indicated in my own research. I have used all of these things, and today I'll be explaining a little bit of maybe network, a little bit of nonlinear dynamics. Okay, and the other things I can talk some other day. So as I was telling you, that when we had the 2008 crisis, people didn't understand why it happened. And that's why there was a series of critical articles written by economists and other scientists. So this one was written by one of my former colleagues, Thomas Lux and Frank Westerhoff. And they said that, economic theory offers policymakers little guidance about what to do in this current situation. This was written in 2009, just after the crisis. And then they said that economics should take stock of the experience of the natural sciences in complex systems with strong interactions. Okay. Similarly, there were another two articles, one in the very prestigious journal Nature and the other one in Science. And again, they were talking about the same things, that the economy, for example, needs, agent-based modeling, or the economic policy needs a interdisciplinary network analysis. Okay, so complexity theory. So people understood that the existing theories in economic finance were not sufficient to understand, okay, or model the behavior. So you had huge amount of data, but there was not enough thing to predict these or forecast these type of crises. Okay, and so physicists and other people have been studying that how to apply the tools of physics to problems in economics and finance, or problems in sociology. So we call these interdisciplinary fields econophysics and social physics. So we were one of the first groups to actually edit a book in 2006 on econophysics and social physics. Okay, and this, for example, shows the traffic system in a small town called Dresden in Germany. This was long time back before. Now you can find these type of maps everywhere because Google actually takes the real-time traffic and plots it. Okay, but that time you would have to do a lot of experiment on traffic and lights and signals and analyze and then make a map like this. Okay, this is way back, more than 15 or 20 years back. And then we were one of the first groups to write a textbook in econophysics, which is now followed in different universities. Okay. And most of my work is actually done on income and wealth distribution, something which I will not talk today, and on limit order books, which is actually how stock prices move in the electronic markets, okay, which are called limit order books. So I'll talk a little bit on this topic. And we've been actually organizing conferences and editing proceedings, and we have worked on several issues. Some of these which I will talk today is like what is systemic risk, network dynamics and all, and the other things I would not be able to talk today. You can also find most of these articles in my webpage. I'll give you the references, and these are based on two review articles that we had written back to back in 2011. And there was another volume of in Science and Culture where 40 different scientists from 30 different countries summed the findings in the field of econophysics. And so if you want to learn more, these are all available as PDFs on the website. Okay. Now, as I was talking, that the financial market is like a model complex system where many agents interact with each other and perform the collective task of finding the best price. Okay, so it's collective behavior, and there are several interactions. That's why physicists are also interested. Why? The physicists used to study collective behavior of atoms and molecules, which are interacting with each other. So we try to understand that are the same tools, can the same tools be applied to the financial market, right? And what we do is we are guided by the experiments, which in our case are stock price movements or economic data and all these things that I was talking about. Okay, and now you will find that most of these financial markets have become completely algorithmic. So it's called algorithmic trading. So these banks and the financial institutions, they have extremely powerful computers where people have already coded, and they'll actually do that. If the price goes above like this and then comes down and down, so they'll code. So if and then they are automated. So they know when to buy the stocks, when to sell the stocks. Okay, so most of the market, actually almost 65% of the stock market is actually working on algorithmic trading, and that's where a huge amount of artificial intelligence and machine learning methods are being used. Okay, now what is important is that this big data has interesting temporal and strong network structure, and that's where I will be focusing in the next 10 or 15 minutes. Okay. So what people are doing are actually looking at the movements of these prices. This is again taken from a slide of my colleague who spoke in the conference, and they were trying to detect these price patterns. Okay, so that's what most of you all try to do in data science, look at the patterns of movements, right? Uncovering pattern recognition. Right? Now, there were two very interesting books and volumes which explain why stock markets crash. Okay, but that's basically like trying to understand, what may go on, but we still don't understand why and how these things happen. So in 2003, the first edition came, and it was written by my colleague Didier Sonnet, who is now in ETH Zurich. Uh, but but in 2017, a second edition came, and it's definitely we've made progress, but we have not solved the problem. Okay, and that's why we need to continue doing till we understand better. Now, the first time stock prices were modeled was by a mathematician called Louis Bachelier. Louis Bachelier, and very few people knew about him. He actually worked under the supervision of a mathematical physicist called Henri Poincaré in Paris, and he modeled the stock price movement at the French stock market called Paris Bourse in 1900. And he said that they are random walk prone. So it's as if you toss the coin. Every time you get a head, it goes to the, it rises. Every time it goes, have a tail, it lowers. So the prices go up and down as if you are tossing a coin. So you may get two heads, so it will rise 2 steps. If you get one tail, it will go down 1 step. And that's like a random walk. Now, Albert Einstein was actually one of the first persons to model this random walk in Brownian motion. And many people thought that Albert Einstein was the first to do that, but actually it was Louis Bachelier. Now, Louis Bachelier's work was discovered by Ito in 1930s, and that's why you have something called a stochastic calculus, okay? Because your normal methods of calculus that you've learned in high school will not work here because things are stochastic or random. And so Ito formulated something called the Ito's lemma, which helps you to actually compute these things, okay? Now, very few people were unaware of that Ito's lemma, and it was only in the 1950s and 60s when Kolmogorov, another mathematical physicist, started actually working with many things like turbulent and chaotic systems and discovered the Ito's lemma. And so you'll often find in science that Louis Bachelier, even though he formulated random walk, he was never recognized for his efforts because in his lifetime, nobody understood his work, nobody appreciated his work. Okay, and that often happens in science, that you have a long gap before people really understand and start appreciating. Now, physicists have studied a lot of systems which are random or chaotic. Econometricians have proposed what are called Arch-Garch models, which are basically stochastic multiplicative processes. But then the financial market has much more complications than any of these systems. That's why for physicists, these are a whole group of new complex dynamical systems. Okay, and that's why we have been studying through a series of papers where we have tried to look at how the stock markets prices go up and down. So how the stock prices move, how the sectoral prices or indices move, how the economic stock markets move, and we try to picture them as different types of networks at different levels. So these are called multiplex networks or temporal networks because we see the evolution of these, okay? And so we have a whole series of papers and where I have studied the same data sets with different techniques. So the first two ones are using what are called the random matrix theory in physics. Okay, and then you will find that in the third one, which is here, I have used a completely different technique based on a statistical physics concept. And then the fourth and fifth one are again two different, different domains, which is called algebraic geometry. Okay, and then we have another one where we haven't published yet. We are writing, which is called topological data analysis. Now I'll show that all the insights that I gain from these different techniques, from different tools, will help me to understand better and better the same market. Okay. So what we do typically is that you have these, for example, there's close price movements, right? So Coca-Cola, you have the stock prices, you have prices for McDonald's. Now, instead of working with price, we work with what are called log returns, right? Because these are stationary. So you just apply this formula on the price and you'll get returns, which are, I make them sort of a mean stationary. It's actually weakly stationary in some form. And then what happens is you can calculate the correlation coefficients. So you can calculate, so I and J are two companies like Coca-Cola and McDonald's, and you can calculate the correlation coefficient. But like that, you have several stocks in a single market. So here I'm showing that how the correlation matrix of 194 stocks. So there are 194 stocks, and these are correlation coefficients, all lying between -1 and +1. Okay, and these are color coded. So the red ones means it's highly correlated, blue ones means it's anti-correlated. And then you see that these are computed over a certain time window, and then we shift the time window. So we see the evolution of the market. And then you'll find that at different periods of time, you have completely different correlation patterns. And then you see such interesting things like in 2011, when the whole market becomes highly correlated. Okay, so we want to see that how this evolution goes. So the correlation coefficient, the distribution of them move. So it changes, the whole market moves. And what are these interesting periods when it becomes highly correlated? We find that those are exactly the periods when we had market crashes. So this was the Black Monday crash on October 19, 1987. Which was one of the biggest crash. Then we had the Lehman Brothers crash in 2008. And then in 2010, another crisis, 2012, another crisis, and so forth and so on. Okay, so what we tried to do is we can look at the mean correlation or what I call the volatility, or what is called the risk or systemic risk, right? And we try to understand how the financial system is working. And what we are interested are in these extreme events. Okay, they occur rarely, but then when they occur, they can have devastating effects, like we saw. Okay, and they can be endogenous causes, or they can be exogenous causes. So the exogenous shock, like the pandemic, it came from outside and it hit the market, and it hit all the global markets equally. Okay, now what we see is that if you look at this sort of a system, we will find that during a normal period, it's very heterogeneous, okay? And there are a lot of modularities, so modular structure. But when the market crash happens, that time it becomes highly correlated, so it becomes homogeneous and extremely connected. So one part of the system will go and affect another part of system, okay? And we will show you more in this thing, okay? So as I was telling, that you can work with correlation coefficients, or you can make a sort of a transformation which allows you to convert these correlation coefficients into distances. Okay, and once I have a distance, I can actually apply many of the common tools and techniques in computer science. For example, drawing like minimum spanning tree, which helps you to convert those correlation structures into pretty network diagrams. Or you give that distance matrix as an input, and this multidimensional scaling algorithm in computer science will give you a map which satisfies those distances. So then you can view the stock market as a map. This was around the 2008 when you see that the Lehman Brothers was behaving completely in a different way, and it was away from the market. Okay, so in the multidimensional scaling, all the things which are behaving very similarly are found close to each other, and when they are far apart, means they are working anti-correlated to each other. So you will find that here is Google and here is Lehman Brothers, and it's probably they are highly anti-correlated. Okay, so what you can do is when you have these correlation patterns moving, you can plot these maps and you can see how they evolve. Okay, now so this is one technique in computer science or machine learning that I'm using. And then what you can do is, for example, compare these correlation coefficients from these matrices, okay, and you can compute what are called distances between these correlation frames, and you can plot that over time. And you will find that whenever the market is very different, that's when you had these interesting events like Black Monday or the dot-com bubble or the Lehman Brothers or the credit crunch or the Euro debt crisis. Okay, so what we do is we take these distances. So this is the distance between this matrix and this matrix, this matrix and this matrix, this matrix and this matrix, and you plot these. Okay. Now I can do that in a larger scale, and you'll see that all these points actually correspond to each of these correlation frames. And then you can use clustering algorithms like the k-means clustering, which you normally use in machine learning. Yeah, and then you will find that there are different types of clusters. Now, if you take any of these magenta clusters, it will look like this one, S4. Any of these blue ones will look like this. Any of the green ones will look like this. And any of the black ones will look like this. So as if there are 4 groups or 4 states in the market. And because I know what the correlation matrix was over time, I can actually go and reconstruct. That means the market must have been in state 1 in this period, and then there were fluctuations up and down. Okay, and once I have constructed that history, I can actually calculate how many times it jumped from 1 to 2, 1 to 3, 1 to 4. Okay, and you'll find that it doesn't go from 1 to 4. Okay, so what you do is now you map those probabilities in a network, and you find that whenever I'm in state 3, there's a high probability of jumping to state 4. So if I'm in state 3, I'll be very careful. So I'll be designing my strategies of investment accordingly. Okay, but if I'm in state 1, I can be pretty sure I will not go to a market crash the next day. Okay, now I'll talk about 2 more techniques very shortly, within 5 minutes actually, so that I have time for questions. One is so I was telling you that we have these correlation patterns. What you can do is you know how the Google page ranking algorithm works. It's based on something called eigenvector centrality. So you can convert this into a network and measure what is called the eigenvector centrality. And then what you do is you can compute a sort of a entropy based on that eigencentrality. And this eigencentrality actually tells you. So if I am in a network, so suppose I have a Facebook network. Right? I have Facebook friends. So I have many connections. I'm connected to many of my friends, but I may have 5 friends, and Sarabjot may have 5 friends also. But my friends are not too famous, and Sarabjot's friends are extremely famous, and they have high connections. So even though we have equal number of friends, he is in a more what we call eigencentral position, because he is connected to very influential people. Okay, so that's what the eigencentrality measures. So it gives you a sort of a hierarchy in that network. So we use that, and we use something called the random matrix theory to decompose the correlation into smaller matrices, which are called partial correlations. And then we compute for these matrices. So these are the matrices which evolve over time. And then you can decompose each of the matrix into smaller matrices. And we look at these structures and you evaluate this. And then what we do is we see how these quantities move. And based on those quantities, we can actually classify each of these correlation frames. And you'll find that all the crashes are these red ones. All the bubbles are interesting, even the light blue ones. The ones which are here are very interesting, called anomalous events. Okay, so what we do is we convert these correlation matrices, and not only we do it for a single market, but we do for different markets. Okay, and then we compare with each other how the things behave. And then what we find interestingly, that there are common features in different markets. So the US and Japan display some of these commonalities. Now you will see that whenever there is a crash, there is a certain movement. And whenever there is a bubble, there is another movement. So I can actually, go through these, and it will be a long video, but I can evolve over time when each of these markets will, keep on, moving. So it will be changing, and you will be able to monitor the health of the financial system. And so whenever there are crashes, these are these red ones which you see. Those are these points which you see here. Okay, so what we see is basically the market keeps on evolving, and you will see that correlation patterns changing, and that is what you will be able to monitor. And when you monitor, you can design your investment strategies, right? And so these will help you to understand what is going on in the market and how I should think. Yeah. So this is when you see the markets moving. This is the Black Monday crash and so forth. Okay. Now, last 5 minutes I want to spend on what is called topological data analysis. So in terms of topology, there is
Anirban, please don't rush don't rush just to keep to the time. We are quite used to webinars going over, so we would rather learn. Okay.
Fine. Thank you. I was actually a little bit, cautioned because I was watching my time.
Please don't.
Okay. So now I will introduce a very interesting concept called topology. So in terms of topology, there is no difference between this coffee mug and the donut. Why? Because if you transform, it will change from the coffee mug to a donut in a continuous form. So a continuous deformation can change this coffee mug to a donut. So there is actually a joke in mathematics that a mathematician cannot actually distinguish between a coffee mug and a donut. Similarly, this cow has the same topology as the ball, because with a continuous transformation, you can actually convert that thing to a ball. Okay, so these are the types of confirm things that you have, and so normally what we do are study these different topological properties. One is called dimension, the other one is called compactness, the third one is called connectedness, and so forth. So what happens is there's an interesting concept called simplicial complex. So you know about points, right? So the points is a zero simplex. Similarly, a line which connects two points is a one simplex. And then a triangle which is connected by three lines is actually a two simplex, and so forth. Now, beyond a certain, you cannot even conceive, because your brain is used to working in the 3 dimensions plus maybe a time, which is the 4th dimension. But if I have a 5-dimensional object, or 10-dimensional object, or 26-dimensional object, then my brain cannot conceive. Okay, but mathematically I can do that. So what they do is study that, suppose I have a data. So I have a data, and I plot them on a certain plane. So these are these data points. So it's a point cloud. Now what I do is I take a parameter and I start making the radius, and this epsilon starts growing. And whenever there is a intersection, I will make a line. And so you will see that how the data is actually there. And what happens is you look at when are these holes appearing, or when are they disappearing, because when you change this parameter, you will see that this thing changes. I'll give you an example very soon. So then what you do is you study that how are the holes appearing or disappearing, or how are certain triangles appearing and disappearing, and they are measured by what are called Betti numbers. Okay, I'm making it very non-mathematical, but it is actually very, very sophisticated mathematics in geometry. Okay, now, like I was telling you, that when I expand this epsilon, you can see the structure changing, and then you actually get to study what is the nature of the data structure. Okay, and so what will happen is that, like, you concentrate here, that suppose as a function of height, this is height, I look at what are the structures. So initially there will be 4 legs, and keep on increasing, and then the tail comes. So then another thing appears. You keep on increasing, and then this was the thing of the trunk of the elephant. And then you go up to a certain height, and then you'll find an elephant. So, but by the time, these 4 might have merged into one. So these 4 will disappear, and a tail will appear. So this is what is called persistent homology. That how long are these structures staying? Okay, how long are the certain holes staying? How long are the certain lines staying? So how long are the certain triangles staying? How long are certain tetrahedrons staying? And that's what is called persistent homology. And then what it does is actually, so the pipeline is you give a data, which is a distance matrix, and then you study this persistent homology diagram. So I'll give you an example. Suppose you have 2 circles without any noise. Okay, then the persistent diagram would look like this. But suppose I have 2 circles which have noise, so I cannot distinguish between one circle and the other. Then the persistent diagram behavior is completely different. And then I will be following these to actually understand that what is the noise in the data and what is not the noise in the data. Okay, so there are stable structures and there are unstable structures. Okay, that is what the persistent homology things will tell you. So when I told you that we have these correlation matrices, you can convert them into these networks or distances. Okay, and then you feed them into this topological data analysis, and you look at the persistent diagrams. And then you will see that during a market crash, which is like this, it will be very different from a normal period where the persistent homology structure will be like this. Right? Okay, now what I can do is each of these have a length. And that's why what I can do is I can construct the average of these lengths, which is called the L2 norm measure, or I can look at the average of H0 or average of H1, which are different homological features. And then I can compare and contrast with the normal matrices or metric things which the financial mathematicians or the practitioners. So that's the return or the correlation that I was talking about, or the volatility or risk measures. Okay, and you'll be able to understand when it is going up, when it is going down, depending on these. Okay. Similarly, what we can do, that I was telling you that these are networks I can make. I can make these networks like this. And these networks are not in a Euclidean plane. A Euclidean plane means if you have a plain paper and I draw a triangle, that's a Euclidean geometry. But these are in much higher dimensional. So these are non-Euclidean geometry, and it's what we call in maths is called Riemannian geometry. Now, these are, again, they have curvatures, like I was telling you. So you have, curvatures. So in a plane, the straight line is the shortest path between 2 points. But if I'm in a curvature, in a curved space, then the straight line will no longer be the shortest point. And that's why I was telling that that's the geodesic, that's called the shortest path connecting 2 points in a curved space. Now I can have a negatively curved space or a positively curved space. Okay, so then the geometry becomes much more interesting, but much more complicated. But then mathematicians have studied for centuries about these type of geometrical features. Okay, so we borrow some of these concepts and we try to apply them in financial market. So one such concept is called Forman-Richie curvature. So if I am given a network, I can actually do some little bit of complicated algebra and reduce it to a certain formula, which will allow me to calculate the Forman-Richie curvature between these edges which are appearing in the network. Okay, and then I compute these curvatures, and then I try to understand what is going on in the market. So this is a paper which has just been accepted, and it's in press in the Royal Society of Open Science, where I told you that as my market evolves, these correlation matrices change. When the correlation matrices change, the distance matrices will be changing. When the distance matrices change, the networks will be changing. And as the network changes, I'll be able to monitor it with this Richie curvature measure. Okay, and then we'll find that these interesting ones are the periods which I was interested. Either they are bubbles or crashes. Okay, and so similarly, we can see what goes just before the bubble or the crash. Now, it's often very difficult to understand when we are in a bubble or when is a crash impending. So these features will actually try to tell you, that how the networks are behaving, how the curvatures are changing, how the market things are changing, structures are changing, and not only the two-order structures, but higher order structures are changing. Okay, so these are some of the concepts which will help you to distinguish between a bubble and a crash. Okay, and so forth and so on. Okay, so this is what we have compared different type of measures in the networks. Okay, and then we showed that these Forman-Richie curvatures can understand a lot of new insights and help you to understand what is going on in the market. Okay, so you can not only look in the stock network within a single market, but in this paper, this again is in press in another journal called Frontiers in Physics, where we studied all the different markets in the globe. So across the globe, we took 69 such countries, and we started looking at how the market prices are there. Okay, and again, you can do it through networks, or you can do through those multidimensional scaling maps, and then you can see that what is going on in the whole global financial system. Okay, and then again, you try to understand that where are these interesting events that are happening. Okay, so in summary, we have found a way to understand when there is a business as usual period, or when there is a market crash, or when there is a bubble. So these are these unstable periods. And then these new insights can help us understand tipping points, or to measure the systemic risk, or to understand when can a network collapse, and so forth and so on. Right? Now, we have come a long way from Euclidean geometry, when Euclid actually formulated the Pythagoras theorem. So that's one. Then there was a second paradigm, which was this theoretical. Then we had experimental things, and now we have the fourth regime, which is the data science paradigm. Okay. Now, perhaps the right way to move is to understand before one predicts. So this is what the he's called the father of artificial intelligence, Herbert Simon, whom I talked about. He was awarded the Nobel Prize in economics. He said that if I want to understand, predict, then I have to understand first, right? And that's where you need to know the science. Okay, so I have data and I need to do the science, then only I can predict. Okay, and so I hope I've been able to convince you that there is a need to bridge the data and science in order to understand these complex systems, or in order to decipher the complexity. So all my papers are available from the Google Scholar web page or from my website in my university. And thank you for your attention.
Anirban, thank you for an amazing talk. It lived up to my expectations and more. I just love the way you have analyzed, the financial markets. And I know this is only one domain that you worked in, right? In fact, we were very lucky to have Kiran also talk to the students a few months ago, or a month ago, I guess, where she talked about looking at terrorist networks and things like this. So I really enjoyed the talk. So thank you for that. Firstly, one question that I had was that the financial markets that you've been analyzing, they are fairly stable compared to the cryptocurrency markets. Has there been any work in looking at whether the same types of analysis can predict how volatility within the cryptocurrency market can be modeled in some way?
Yeah, there have been several studies actually, including the one which I showed you, Professor Didier on it. They have a paper in Royal Society Open Science Journal, which worked on this Bitcoin currency and all that. And my student Vishwas actually is working on that, on Bitcoin currency.
Okay, brilliant. So, we do a lot of work in Tatras in this area, and actually a bot that does trading. So, this is something that I'm going to pester you with, and we must work on together.
Sure. Right. And that's a very important point you mentioned, because here I focused on the financial market, but the same tools can be applied. We have studied in the environmental system. We have applied it in the EEG brain, EEG signal,
right? Yes.
Electrodes. We can work in socioeconomic data, like I showed you, or like what Kiran might have told you about the terrorist network or ethnic conflict network. So a whole variety of things. And that's why, even though they are very different systems, and that's why all of them are complex systems, you can find that there are a lot of features which appear or are similar in many of these different systems. And one goal of the complex system scientists are to understand that what are the universal features. Okay,
right.
So that's a very, very interesting point that you reminded me.
Now, when I looked at the one of the graphs that you had in the financial markets, right, where you were showing the different states of the market,
right?
S2, S3, and S4, you're calling it. And then somewhere around 2002, it seemed like there was a shift, right, where the need was for the market to be sitting in the S1, and then it suddenly moved to S2 and never really returns to S1, right?
Absolutely. You have an extremely good observation. let me you hit the right point. And
right.
Okay, I may need to share my screen again, I think.
That'd be great. Yeah.
And I'll take you back. What you observed was fantastic. Actually, that's true. If you'll see here also, or any of these features. So 2000 onward, it actually became extremely volatile. And here I'm showing for the US market. In Japan, it was observed in 1990. 1990 onwards, it has been very different in the Japanese market. Okay, so you will actually be able to understand that something must have changed in the way the financial market worked in those countries.
Right.
Okay, yeah, you are absolutely correct about that.
Are we able to explain what has changed?
Yes. So there were certain regulations. Yes. Regulation changes.
Right. Okay, great. So there's a question from Achintya. He says, sir, how much data is required to predict such findings in the financial market? How to monitor it?
Right. So it depends on actually what you want to do. We have worked with what are called intraday data. That means every millisecond the prices are changing for every stock, right? Now to work with that data, intraday data, and that's called high frequency data because it's coming every millisecond. It's very difficult because huge amount of data. In a single day, you have gigabytes of data and you have to analyze that. And to make predictions in that scale is much more difficult. But if you work, for example, at the daily return level, that means at the end of the day, you will find these prices, quoted in newspapers or, flashed in the new television. So you have the stock prices at the daily level recorded. And then over several days, you monitor, and then you can apply these techniques and do it. Okay. Now, we have applied these similar techniques in intraday data also, but that's what I'm saying, that two things will change. One is the time scale is changing. Right? And that's why some of the features that you see in that short time scale may not be present in the longer time scale, or what is present in the longer time scale will not be present in the shorter time scale. And that's a very good question, because I want to point out, for example, at the daily level, you might find that the prices of Coca-Cola and Pepsi are correlated. But when I go to a high frequency data, the stocks are not traded simultaneously, right? So that correlation disappears. So when you go to higher and higher frequency, the correlation will actually go down like this. And that's an effect which is called the Epps effect. So at the lower scale, you will not see actually correlation, but it is there at the higher scale. And that's why I was telling that for understanding this is very important. You have to understand what is the time scale you're looking at, or what is the length scale you're looking at. So some of these features will be present in certain time scales, and it will become completely unimportant at a different time scale. Right.
And that's a very interesting life lesson as well, right? Sometimes when you're too close to things, you feel that everything is chaotic.
Absolutely.
You need to move out and look at it from a macro level, and you see probably the patterns that will help you, right? So thank you for that life skill as well. One thing, again, coming back to the financial markets, the number of crashes in the financial market are small comparatively, right? There was, I guess, 30 years data almost that you were showing.
Yes.
And there's a small number of crashes. Now, how sensitive are the kinds of analysis that you were doing to the number of such extreme kind of events, right? Because typically machine learning, we talk about the class label being skewed, being a problem, right? And you're trying to then address that in some way. Is that the case here also, or not so much?
Most of the methods that we adopted here, and that's why I was saying and actually showing, because when we published one paper using random matrix theory analysis, one of the referees refused to believe that we had the number of crashes increasing in the last decade. So you'll see, I showed you that there were a lot more crashes in the last decade, than the previous. And he was saying that how can that be true? And then I had to tell him that, see, it's not that I am telling that the crash happened, right? The data is telling that. Now, the problem is often it's difficult to define a crash. So you'll find even with 2.5% fall in the index, you have a crash. Sometimes with 10% index drop, also you will not have a crash.
Right.
So just by looking at the fall, which is the return, you cannot actually tell you are in a crash or not. And that's why we were saying that you need to have a whole new way of looking at the crashes. So you study the correlations that will help you to study better, or you understand these features that I was telling you that will help you to classify whether we are in a crash, or we are in a bubble, or we are in an anomaly, or we are in a normal period. Okay. So the new methods that I showed, and that was the work with Richie, it automatically, depending on the features of the market, it automatically classifies them into events. And what we have found that they are pretty robust. So, with the slight changes in the noise or outliers, it will not change. It will not change. So they're pretty robust.
Very interesting.
Did I answer your question that you wanted to understand whether outliers can have effect or whether they are sensitive?
Right. So, a very skewed distribution in terms of, what is, a crash versus a non-crash, right?
Right.
You're saying. Harmanpreet is asking, sir, RBI has decided to launch the cryptocurrency, and there will be number of days then. How we reduce the complexity? I mean, how do we get the valid information out of it?
Okay. So one is, I just read last week that the government has announced to ban private cryptocurrencies. and
so it makes it easier then, right?
Many of them are gone. And actually, the problem is that we still don't understand, how these currencies are working, and what is the thing going on, what are they driving this price volatilities that you were talking about in the bitcoins and thing, and whether they have similar. So some of my collaborators in Mexico are studying the correlation between the movements in the stock market, the equity market, and the Bitcoin or the cryptocurrencies, right? And you might find that there are some correlations. So when this becomes more volatile, it influences the other. But there might be a time lag as well. And then, so these are very interesting questions. Now the thing is, what you are saying, that how do we reduce the complexity to understand? You can't reduce the complexity. The only thing what we can do, like what you do in normal data science also, you have huge number of huge dimensional data, but then what I do is I project into a lower dimensional space and then try to understand what's going on, right? So most of the tricks that I was showing also is basically effectively reducing the dimension, but we don't reduce the complexity. The complexity is there. We try to capture the complexity using these type of
less dimensions, right? Very good. Okay, another question here. You can see these, or shall I read it out?
Yeah. No, I can see that, and that happens to be my student in master course. Actually, I told them to. It's Banti Virwani. They have started. They joined my course on Monday, actually. So.
Oh, okay. Nice.
Yeah. So, are the causes organic or manipulated too? No. The thing is, in the cryptocurrencies, it's very difficult to manipulate, and similarly in the stock markets, what happens is like this. So, there's very interesting things. Like I told you, that these are complex adaptive systems, right? Now, suppose Sarabjot and I design a strategy where we can make money. Now, if we keep to ourselves, we'll probably able to keep it, make some profit. As soon as others start to understand that we are up to some trick, and they figure out what the trick is, they will start applying, and then I will not be able to take advantage of that, right? So that's what we call arbitrage, statistical arbitrage in financial market. So suppose I find that, okay, in JNU, the price of oranges is 20 rupees, and in Connaught Place, it is 40 rupees. Right? Now, two things can happen. As soon as the dealers there understand that, they will either have to lower, because they have to compete with orange sellers in JNU, or the JNU people will increase the prices and make it 40, because they can take advantage of it. But once this is discovered, it will take, it can go either way, but nobody can take advantage of the price difference. Okay. And this is what is called the efficiency of a market. Now, if a market is very efficient, so you will not be able to take advantage or make statistical arbitrage. So there is actually a whole field of research which is called the efficient market hypothesis, and that studies how efficient the market are, how efficient the markets are, and that's what they say, that if there is a certain amount of information, the market will react in such a way that nobody can take advantage of that information. Or even if you can do it only for a very small period. Now, so it is very difficult to manipulate and keep it, because others will soon discover, and then, that arbitrage.
Right. But at the same time, there is in cryptocurrencies, there is a lot of collusion that happens also, right? Because it's an unregulated market. People with large amounts of money invested will collude to move the market. Right? How do we?
Right. So what you're saying is that it may be biased towards people who have huge amount of computation. So you and I will not be able to compete with those players who have that, and that's true for equity markets also. So I was telling you that most of the trading that is going on is called algorithmic trading.
Yes.
So all the big banks and financial institutions, they have huge computational power, and they are beating the individual players like anything. And that's why now a whole debate has started in the European Union, that whether they will allow small individual players like you and me to enter the stock market, because they know that we cannot compete with the financial institutions or the banks. Right? And so is it ethical? I mean, knowing that I will not be able to compete with them, should I be allowed? Because I'll go and I'll lose my money. Right. Yeah. So this is more like an ethical issue, right? And they're debating whether they should allow that.
Interesting.
And you won't believe, so most of the stock markets work in a basis called FIFO, first in, first out. So if your order, so I want to buy such a stock at such a price and thing, and so many units, if my order arrives before yours, mine will be executed before yours.
Right.
So when I was in France, the head of the BNP Paribas, Stefan Teach, he opened a company which uses radio signals to communicate, and they were faster than the fiber optics thing. So he moved to New York, and he was able to place those orders faster than the other computers. And if you are a few nanoseconds or milliseconds faster,
That makes a
you will
difference.
be making millions of dollars more than I. So it's that's what I'm saying. So a player like you and me will not be able to compete with such persons, right?
Right.
And then now a question arises whether I should be allowed to think, because I will probably lose, right? And that's where the ethics and all come.
Yeah.
So there's another question from Rahul Bhatnagar, I think. It says that additional computational power or robust algorithm will provide us with prediction. Yeah, I mean, every day we need more and more complicated thing. Two reasons. One is the size of the data is increasing, right? Every day you will find more and more. So like I was telling you that now people try to combine the movements in stock prices with news or sentiment analysis also, right? And I know that if you want to do sentiment analysis, you'll have to do, analyze all the data coming from Twitter, from Facebook, from WhatsApp, all these things. And then that's huge amount of data. So you are trying to link something in the news or sentiments with the stock prices. Both are very, very thing. And then you need very heavy computation to work these things out.
Okay, well, Anirban, I had a couple of kind of interesting thoughts also very early on in your talk where you were talking about science. I wanted to get your view. I mean, one of the problems that data scientists have, and I don't know whether the term scientist is right for what we do, but we don't have control over the data generation process.
Mm-hmm.
So when you talk about that, process that science follows, where you have a hypothesis and then you do your experiments, often the data that's given to us, the experiment has already been conducted, right? In that sense that, we don't have control over that. So, how do we bring in this concept, I mean, of being able to really experiment and create conclusions that are not purely data driven and are closer to scientific learnings?
Right. Very, very nice thing. Point. Two things. One, I wanted to comment on the thing that you told. So there was one of my friends who told that anything which is truly not a science actually needs this word science behind it. So you have computer science, social science, data science, because that's not truly science. So you have to add that word science. So physics is something which doesn't need a word science behind it. Okay, but that's a joke. Don't take it that way.
I agree.
Yeah. So the thing is, so that just take it as a joke. I have no offenses meant to anyone.
Not taken.
Yeah, you have made a very nice thing that in science often I can design certain experiments, make observations, and then try to think. But in science itself also, there are two things. Sometimes we make theories which cannot be experimentally verified so easily. So string theory is such a beautiful mathematical theory, but it is not experimentally verifiable.
Right.
On the other hand, sometimes what we have is we have experimental data which we cannot explain because we don't have the proper theory. And that's how the physics works, So sometimes the theory is, at an advantage. Sometimes the experimental thing is at an, advantageous position. And there is a lag between the theory and experiment. When the lag is positive, sometimes the negative. Okay.
Right.
Now the same thing is happening here also. Sometimes, people had the theories and then, empirically you'll be tested. But in social systems, like I was telling you, it's much more difficult to verify experimentally. And one sense is because it's also an adaptable system. And that's very important in the case of financial market, for example. Suppose I predict that there is going to be a crash on Wednesday. What will happen? The people will immediately panic, and then the crash might happen on Monday.
Yes.
Right. So I will not be able to prevent that crash anyway. I predicted it for Wednesday, and what will happen is I actually put that information in the market. Market reacts, and then the crash will happen on Monday itself.
Right.
So you have no control over that, right? Because we are in a complex adaptable system. And the problem is to design experiments is very difficult here. And so And sometimes you can see the effect immediately, but sometimes it takes long time. So if it's a public policy that we make based on, for example, economic data analysis, sometimes if a government introduces a measure now, a policy change, it will take several years for us to understand whether that's a good thing or not. And that's why it's very important to do probably simulations or analysis and try to find out what the scenarios can be. Yeah. So we are at a critical juncture, for example, in India, where, for example, these farm laws have been designed. Now, whether that will be successful, so these farm laws, whether it will go to advantage of the farmers or it will go to a disadvantage, no, people are not clear. And that's why there is so much doubt, confusion, so much protest and all these things going on. Right? If I were able to do experiments, I would have done that, seen the effect, and then frame the policy. But I can't do that. I can't do that. Right? And that's a severe disadvantage in the field of social sciences. But with these computational techniques, maybe we can make models. Maybe. So in my course actually on complex systems in JNU, I teach those type of models, how social science models can be built, and they can be mathematical model, and then you can do simulations to understand what can happen. Okay, but life is certainly more complicated than the models that we build or we
Yes. Okay, great. Thank you. There is another question around the time span of data for monitoring. Is that just another variable that we need to kind of hyperparameter that we need to look at?
Yes, that's what I was saying, that it will depend on what effects you're looking at, what times of the data, what questions you're looking at. And sometimes it's very difficult to understand. So you had the flash crash in 2010, which was on a Friday, May 5th, I think. It happened within minutes that the people didn't know how to actually react, because it was set off by something in wrongly done code in algorithmic trading, which set off that crash. Okay, and people didn't understand what happened and how to control it, and then the markets crashed. Sometimes it is in the time of orders of hours or minutes. Sometimes it takes a longer time to and so you often see that bubbles appear for a period of few years, and then it bursts. When it bursts, and then you have a crisis. So it can take several years, and sometimes it can take only several hours to react. Okay, so it's very difficult to understand, and it all depends on what you are interested or what type of training you're doing and all that type of things.
Right. I think the questions will never end, or questions will never end. But of course, we are taking too much of your time here. It's almost an hour and a half now, so we'll try and not be greedy and let you go, Anirban.
Right. This is to the students this is for the students that if they think that they want to learn everything in one session, that's not possible. And I'll be happy to return, whenever Sarabjit calls me, I'm available, and I'll be happy to interact and share many other topics.
You may live to regret that offer, because ask you very frequently, because it's been a really amazing webinar, and thank you so much, Anirban.
Thank you very much.
Bye-bye.
Bye.